Good morning, ladies and gentlemen. Today, I'd like to talk about a two-axis tactile sensor with 1 micron diameter tip of contactor for detectionability of micro-region surface texture. I'm Kazuki Watatani. I'm a graduate student, Kagawa University, Japan. Recently, various tactile sensors aimed to realize human tactile sense have been developed and reported. Tactile sensors that have cantilever embedded in PDMS are high sensitive. However, detection performance of the micro roughness is poor, since continuous rubber structure is used. On the other hand, tactile sensor using polymer film such as PVDF is difficult to use for independent sensing of the shear forces and contact force. Therefore, we have developed a multi-axis tactile sensor which can detect two-axis motion independently. This device was able to distinguish different types of samples with their output waveforms of surface shape and frictional force. So, promising method of tactile sense quantification was demonstrated by the previous device. However, obtainment of surface texture below around 10 micron roughness has not been achieved. Since human's fingertip can discriminate surface texture finer than 1 micron, it is considered that a higher resolution of tactile sensors is required for quantification of tactile sense. The narrower the contactor tip, the higher the spatial resolution. This figure explains behavior of contactor tip on micro surface roughness. Since our previous device has 200 micron diameter, it cannot follow the small roughness in the figure. The motion of the contactor draws envelope-like curve of actual surface shape, and high-frequency signals are finally lost. This figure shows the output waveforms of our previous tactile sensor with 200 micron diameter tip. The surface roughness below around 10 micron has not been obtained. If the contactor tip becomes narrower than the previous device, the locus of the tip motion gets closer to the actual surface shape as shown. The spatial frequency of the device depends on the tip diameter as shown in this diagram. Decreasing the diameter of the contactor tip, the cutoff frequency of the roughness sensitivity shifts to higher frequency region. Since smaller pitch of roughness can be detectable. Considering the fact, in this study, a new design of tactile sensor with 1 micron diameter tip of contactor has been developed to enhance the detectionability of higher spatial frequencies. This figure shows the configuration of the device newly developed in this study. It consists of a narrow tip of contactor of 1 micron diameter, two suspension units for independent detection of two axes, and a chip frame including overland stopper. Contactor chip protrudes from the plane of the chip edge by 50 micron. Detection circuits of full-bridge piezoresistors are integrated by ion implantation process on the suspensions made of single crystalline silicon. Individual axis detection circuits detect both the depth displacement and the local frictional force at the contactor tip. The chip frame side functions as the height reference of the contactor, which is called the reference plane. Next, I'd like to explain the sensing operation of the tactile sensor with sweeping motion. Sweeping the contactor on the surface of the measuring sample The contactor moves vertically according to surface micro roughness. On the other hand, the contactor moves in parallel to the surface according to the local frictional force, which is caused at the same point at the same time. Analyzing the relationship between the surface roughness and the micro frictional force generated at the same point, micro-region's surface texture around a few microns will be obtained thanks to the very narrow tip of contactor. The tactile sensor device with small-sized contactor tip was designed and fabricated by SOI wafer with 15-micron thick active layer. The size of the sensor chip is 3.1 times 4 square millimeters. The tip diameter of the contactor is designed as 1 micron to realize higher spatial resolution as explained. Piezoresistors are integrated on two 20-micron width suspensions. Full-bridge configuration of the detection circuit is employed to improve the sensitivity and SNR as compared to half-bridge configuration in our previous device. The device was successfully fabricated as shown in this slide. Integrated piezoresistor detection circuits are formed on the 20-micron width suspension beams, and the 1 micron diameter tip of contactor shape is precisely fabricated as designed. This figure shows the experimental setup of device evaluation. The sensor device is fixed to the opposite side of the measured sample, and the measured sample is fixed on the one-axis linear motion stage controlled by a measurement PC. This movie is showing the actual sensing motion of the tactile sensor in measurement of operation. The contactor tip and the reference plane is pushed to the sample surface, and the sample on the movable stage is swept from left to right. The scanning speed is controlled to 1 mm per second in this experiment. As we can see, suspensions are moving in the two directions according to the local area roughness and the frictional force. The measured waveforms of surface roughness, shape, and frictional force using the fabricated device are shown in this figure. In the first pressing motion, the contactor is pressed up by the object without sweeping. Since response of the frictional force signal is not observed, it is confirmed that the cross-axis sensitivity between the two axes is very low. Measured sensitivity of surface shape at a 10 volt supply voltage is about 2 mV per micron, which is 2 times higher than the previous device. The waveforms under the sweeping motion are shown in this region of figure. The signal on surface shape is changing according to the micro roughness of the surface. At the same time, the signal of frictional force at the micro contactor tip is obtained as the blue-colored line in the figure successfully. In order to verify the improvement effect of spatial resolution, the output of the device is compared with that of the previous device with 200 micron tip of contactor. Surface shape waveforms measured with a stylus profiler TAC8 is also compared to use it as the reference performance. This figure shows comparison of each output waveform. Since all the results are obtained from the different point on the same sample surface, the shape of the waveforms should be different. As seen in the figure, higher frequency components are included in the output waveform of the device with 1 micron contactor tip. The device in this study have realized a higher spatial resolution than the previous device, and the obtained spatial resolution is similar to the high-performance stylus surface profiler, including the special function of frictional force detection. Finally, I'd like to conclude my talk. In this study, the two-axis tactile sensor with 1 micron diameter tip contactor was fabricated, which is able to detect microsurface texture. Output sensitivity to the surface height was 2 mV per micron, which is 2 times higher than our previous device. The new device has realized a higher spatial resolution than our previous device, which is similar to that of the stylus surface profiler. Additionally, our device can detect the micro friction generated at the contactor tip at the same spatial resolution. This sensor will be a very effective tool to quantify the tactile sensation of humans' fingertips. Thank you very much for your kind attention.